Okay guys, let's finish this problem. I said D is negative. It's not inconclusive. Remember, when D is negative, this is a saddle point. If it's a saddle point, we don't have much else to do at 0, 0. What about at x to pi over 2x? If we let y equal pi over 2x, what are we going to get? If we're substituting y as pi over 2x, I'm just going to convert this. This would be negative pi squared over 4x squared times the sine of pi over 2. Which is sine of pi over 2 is 1 times negative pi squared over 4x squared. So it's just a negative pi squared for 4x squared. Fyy is negative x squared times, again, the sine of pi over 2. So that would be times just negative x squared. So this whole thing, negative times negative is positive, the x squareds cancel, would be pi squared over 4. What about this thing? So let's talk about f of xy at x pi over 2x. We get negative x times y, so that'd be negative x times pi over 2x, that's negative pi over 2, times the sine of xy, which we already know from this one, these things, is 1, plus the cosine of pi over 2, which is 0. So this thing is negative pi over 2. So I need to take those two things. We have pi squared over 4 minus this negative pi over 2 squared. That was just pi squared over 4, so this whole thing is 0, which we say is inconclusive. Now, are there alternate methods for us for figuring out what we can do? Well, let's talk about sine of x times y. From the closed interval 0 to pi, 0 to 1. Sine is always positive. Sine is always positive from 0 to pi, and those are all the things we can possibly multiply by, because we go from 0 to pi and 0 to 1. So if sine is always positive, what happens when we plug in a number like this to sine of xy? We get sine of pi over 2. But sine of xy, by the way, is also greater than or equal to 1. What do we know about sine of pi over 2? When I plug in x times y to be pi over 2, we know we get exactly 1. So this has to be a maximum by logic. There's no way for it to be a minimum. Now, when we said we plugged in 0, 0, we would get 0. Well, we know sine has to be greater than or equal to 0, so that means even though this thing was a saddle point, it's kind of a relative minimum if it could keep going on the side. Because in the reality, the thing about 0, 0 is it's actually one of our boundaries here. It's one of the boundaries x 0. Now what do we know about all of these sets of boundary points here? If y is 0, we're taking the sine of 0, which is 0. So we fill these in. This is 0, this is 1, this is 0. If y is 1, we just get the sine of x. The sine of x could be anything. I don't know why I called it x. So x from 0 to pi. So sine of anything from 0 to pi could be 0, could be 1. But if it was pi, if it was pi over 2, so pi over 2, 1 for y, would be a potential maximum. So we would have pi over 2, 1 as a possible maximum. But what we have as potential minimums, we would have 0, 1, and and pi 1. Now, what if x is 0? Then it doesn't matter what y is, because the sign of 0 is 0. So again, 0y is a min all the time. x0 along that whole boundary is a min. Now when y is 1 though, you have some maximums. Now what about if x is pi? Again, if x is pi and y is 1/2, you would have a maximum, because then it would be pi over 2 on the inside. However, what do we notice about everything here? When we have x equals, if we let x and y be x and pi over 2x, what happens when x is 1? We have 1 and pi over 2. We can't. I mean, what happens when we let x be pi over 2? We have pi over 2, 1, so this is already included. And here, if we let x equal pi, then we have pi and 1/2. So these two kind of things, the maxes are all included. These other boundaries, though, when x0 and 0y, all along those lines, it should all be 0, and they should all be minimums. So what does this thing actually look like, the sign of xy in this region? It'd be kind of like hills, but let's kind of draw what the picture looks like. Now, we're only going from 0 to 1 for y, and 0 to pi for x. We know the height can't be any bigger than 1. So we know at 0, 0, we're here. So what's actually happening is we said along the line wherever x or y is 0, we're kind of at a flat point. So these would be both flat. Now, but along the line where, for example, x is pi, what we're going to have is little ripples that reach the height of 1. I should draw it smaller, but we know at the end here it's back down at 0. Similarly for y, we'll have little ripples that make kind of like hills. So what kind of creates is like this diagonalized ripple pattern all the way along, where we get to lows of 0 and we get to heights of 1. It's hard to draw ripples going this way, but there are ripples all over a bunch of hills. If you want to see what sign of xy looks like, I would encourage you to go graph it, and that's the end of 13.8. And we'll start 13.9 in another video, which is word problem applications of this exact same thing we're just doing.